Hi, this is Abhinav, and today I'll be giving a presentation on evaluation of convolution coding in OFDM systems. I'll start off with an introduction to the OFDM, then I'll speak something about the channel coding, the convolutional coding, the Viterbi decoder, and something about the interleaver, followed by I'll discuss the modulation techniques which are generally used in wireless communications, followed by the simulations performed in the MATLAB, then the results and the conclusions. Orthogonal frequency division multiplexing is a multi-carrier modulation technique which is generally used to achieve high data rates and to mitigate intersymbol interference. The conventional frequency division multiplexing involves the division of the available band into subcarriers and into subbands where each subband is assigned to a single subcarrier. To mitigate the ISI, a guard band is placed between the subbands, and hence the spectral efficiency is very less for the conventional frequency division multiplexing. Whereas in the case of OFDM, the subbands are overlapping and the intersymbol interference is mitigated by ensuring that the subcarriers are orthogonal to each other. This shows the spectrum of the OFDM symbol, and it can be seen that the component of one uh, of the subcarriers at the center of the other subcarrier is 0, and hence this ensures the ISI is mitigated. This block diagram shows the conventional OFDM transmission system with implemented with oscillators and coherent demodulators. The sequential data is fed to the encoder, and after it is encoded, it is given to the serial to parallel converter, which converts the serial data into parallel code words, where each code word is multiplied by the orthogonal frequency, which are combined and sent over the channel. And at the receiver, the received signal is fed to different coherent demodulators, where each code word is transmitted over a single frequency is demodulated, and then it is integrated over one symbol, and the transmitted data is recovered. This shows the implementation of the OFDM system using FFT and IFFT blocks. The IFFT at the transmitter and FFT at the receiver ensures that the subcarriers are orthogonal and the ISI is mitigated. The data before being fed to the OFDM modulator or demodulator, it is encoded to overcome the errors in the channel. The errors in the channel can be random errors or the burst of errors. And conventional coding is one such technique which is very robust against random errors. In conventional coding, the encoder is specified by three parameters, which is the number of inputs, the number of outputs, and number of memory registers. And the rate k by n is known as the rate of the encoder, which is the number of inputs by the number of outputs. As the rate increases, that is, if each input is uh, expressed with more number of elements, and will ensure that the Hamming distance between the output symbols is more, and hence the error performance is better. The data encoded with the conventional encoder is decoded with a Viterbi decoder. A Viterbi decoder has three main components, which is the branch metric, the path metric, and the tracebar path. At each stage, the received symbol is the Hamming distance to the received symbol with the available symbols is measured, and the symbol which is closest to the received symbol is decoded, and hence as we move along the trellis diagram, and as we receive the final symbol, a traceback path will calculate the path with the least path metric or the least distance, and hence the transmitted sequence is decoded. As it is earlier, the conventional encoder is very robust against the random errors, but in the case of burst errors, the conventional encoder has very poor performance because as sequence with the sequence of errors, a different path will be selected in the trellis diagram, and hence the transmitted bits will be decoded erroneously. To overcome this, an interleaver is employed at the transmitter where the data is shuffled, which ensures that the burst errors are uniformly distributed, and hence they are converted to random errors, which can be taken care by the conventional encoder. The commonly used interlevers are the rectangular interleaver, conventional interleaver, random interleaver, and this random interleaver. The data before being sent to the, before it is given to the OFDM system, it can be modulated in the baseband by some of the common digital modulation schemes, which are the PSK, ASK, FSK, and QAM. In PSK, the phase of the carrier is varied. That is, each symbol is represented by a different phase, and in the case of QAM, each symbol vary in both phase and amplitude, and hence the performance of the QAM is better than the PSK for a given SNR. This slide shows the constellation diagrams of the BPSK, QPSK, and the QAM. It can be seen that as we move to higher levels of modulation, the distance between the symbols increases and decreases, and hence the error performance decreases. This is the OFDM transmission system which is considered. First, the data is encoded using a conventional encoder, and it is modulated by using any of the BPSK, QPSK, or QAM modulation techniques. Then it is converted to the parallel from serial. It is converted to parallel code words, which is fed to the IFT modulator, and the cyclic prefix is actually inserted to mitigate the ISI. The length of the cyclic prefix must be equal to the largest delay in the channel, which is then converted again back to the serial and sent to the channel. At the receiver, the reverse operation of the transmitter is performed, and hence the data is finally recovered. The convolution encoder. For our simulations, I have considered two convolution encoders of rates 1 by 2 and 1 by 3. The output is determined the generator sequence, which is the way in which the inputs and the previous values are added up. Here in this case, the first output is equal to 1 plus d square, which is the first and the bit after two memory elements. These are the parameters of the system considered. For the OFDM system, we have considered 52 bits per symbol and 64 subcarriers, and hence and the modulation techniques which are used are the BPSK, QPSK, and 16 QAM, and a total of 1200 symbols are considered, which is equivalent to 62,400 bits. And for the convolution encoder, two convolution encoders of rate 1 by 2 and 1 by 3 are considered, and the generator sequences which determine the way in which the bits are added up to give the output are taken as 1 plus d square and 1 plus d plus d square for the first encoder, and 1 plus d square, 1 plus 1 plus 1 plus d plus 1 plus d square, and 1 plus d for the second encoder. Coming to the simulations, this figure shows the error performance of the uncoded OFDM. It can be seen that the BPSK and QPSK have almost the equal error performance, whereas the QAM has worse performance compared to BPSK and QPSK. This plot shows the comparison between the rate 1 by 2 and 1 by 3 encoder. It can be seen that the 1 by 3 encoder gives better performance compared to the 1 by 2 encoder. Generally, encoders of up to 1 by 8 are considered unless if, it is unless in the case of the deep space communications where up to 1 by 100 conventional encoders are used. This figure shows the performance of a 1 by 3 rate conventional encoder and the decoding with the Viterbi decoder for different modulation schemes. It can be seen that the BQSK and QPSK should give the better performance compared to the 16 QAM. The OFDM system and the conventional encoder and the Viterbi decoder are then integrated, and the performance is evaluated. It can be seen that the rate 1 by 2 encoder gives worse performance compared to the rate 1 by 3 encoder, but the overall performance is far better compared to the uncoded OFDM. And finally, we compare the performance of a 1 by 3 rate encoder for different modulation schemes. It can be seen that the rate 1 by 3 encoder with BPSK modulation gives the best performance of all the coded and uncoded modulation schemes. And hence it can be concluded that the forward error correction techniques significantly improve the performance of the OFDM systems. And in the encoders systems, rate 1 by k of rate 1 by k, as the larger the k, the better is the performance. And while comparing the performance between different modulation schemes, it can be seen that the BPSK and QPSK, which have the same bit error performance, gives the same bit error performance, which is the best compared to any other higher order modulation schemes. And when we calculate the symbol error rate, BPSK gives the best performance. These are the references which I have used. Thank you. Hi, these are the MATLAB figures which I have used. These are MATLAB codes which I have written. Initially, I've taken different subcarriers and have initialized all the parameters. Then the random data is generated and it is convolutionally encoded, which is then fed to the IFFT block, which is the OFDM transmitter, and then it is transmitted over the AWGN channel. And after it is received at the receiver, the OFDM demodulation is performed, which is then fed to the Viterbi decoder, which does the decoding of the data encoded with the convolution encoding, and finally the error performance is measured. Thank you.